Another energy problem. This time we'll throw a spring in there to give you a little practice with that. First thing I do is draw a picture, and I've done that for you already. I've got my inclined plane, my mass, my spring, and I've even sketched in an initial and a final condition. So in the initial state here, you'll see the mass is already drawn in, and the V initial is equal to 0, and it slides down the incline some distance delta x, and I've got a dashed box here for where it comes to rest. Again, V final equals 0. So that's the situation we're looking at, and while that mass is sliding down the incline, there are certain forces acting on it, and I've drawn a free body diagram for that. The spring is pulling up the incline, kinetic friction is pulling up the incline, the weight in the x direction is going down the incline, and the normal force and the weight in the y direction are normal to the inclined surface. So the first thing we want to check before we get going here solving this problem, I'm kind of assuming this block is actually going to start moving and go down the hill, otherwise the problem will be finished very quickly. But let's make sure it goes down the incline when we let go of it. So let's start at rest at the top. Block's at rest, and what we want to do is see if it actually starts moving. Free body diagram. We're going to have a normal force and a weight in the y direction. There's the weight in the x direction going down the incline. There's no spring force right now because the spring has not started to stretch yet. It's not stretched or compressed. It's in its equilibrium position, so there's no spring force, but there is a friction force, and that's going to be going up. That's a static friction force. And so we know if the weight in the x direction is greater than the maximum static friction force, then it's going to slide down. So let's take a quick look. The weight in the x direction is mg sine theta, where theta is the angle of the incline with respect to the horizontal. And I got 630 newtons when I plugged in the numbers that are given. And let's take a look now at the maximum static friction force. That's going to be the static friction coefficient times the normal force. And the normal force is the weight in the y direction, which is mg cosine theta. I got 450 newtons. So the weight in the x direction is greater than our maximum static friction force, so it slides. Alright, good, because now we have a problem we can work. And this reminds me of an energy problem, because we've got a situation where something's moving. We've got basically what we have is an initial state and a final state, and stuff is happening in between, but we can account for what happens in between with the work done by friction. And so let's take a look at energy, using energy conservation to solve this problem. So we know that the initial mechanical energy conservation tells us the initial mechanical energy would be equal to the final mechanical energy if there were no other external forces reaching into the system, and if there were no non-conservative forces in our system. If we have external forces, we have to account for that by adding a term on this side, on the left side of our equation, to keep that equality. And if we have non-conservative forces, we can add a term. And you want to think about whether it makes sense to add it to the left side or the right side. if external forces do work, positive work on our system, the system gains energy. So our final energy would be more than our initial. So we have to add some term to the left side of this equation to keep the equality. And if our system loses energy through some external force, then that would be a negative quantity. We'd end up with less energy at the end. So it makes sense to have that term, the external work term, on the left side of the equation. How about the work done by non-conservative forces? We're always going to end up with less mechanical energy at the end than we started with because of non-conservative forces in our system. So if we have it on the left side of the reason we put it on the left side of the equation is because this is a negative number. So I always just write that there to remind myself that that's a negative number, because otherwise I'll forget the minus sign at the end and make a mistake. So there's my equation, and I'm just going to go ahead and sort of generically put in what I know for mechanical energy. I only know of 3 types of mechanical energy right now. I can have some kind of elastic or spring potential energy at the start of my situation here, my initial condition. I can have a gravitational potential energy in my initial state, and I could be moving. I could have a kinetic energy, and that's it. Those are the 3 types of energy I know about. Work done by external forces, work done by non-conservative forces. This is negative. I'm just going to remind myself of that. And I could have elastic, gravitational potential energies in my final state, and I could have kinetic energy in my final state. So there we have it. Now what we have to do is define our system, because if we define our system in some ways, then some of these terms go away, and if we define it in other ways, other terms go away. So we need to define our system so we don't double count anything. And usually the easiest way to do that is to make our system and the Earth all together. So it's all part of our system. There's our system. And by defining it this way, by including the Earth, we will use gravitational potential energy to account for those internal interactions between the Earth and our mass. And we won't have any external forces. So what this tells us is no external forces. If we have no external forces, then we can't have any work done by external forces. So I'll call that 0. We also know that at the initially the spring is not not stretched, right? So I've got no spring potential energy in my initial state, and we know it's not moving in either the initial or the final state. So I've got no kinetic energy initially, and I've got no kinetic energy at the end. So there is friction, so we need our work done by non-conservative forces, and we know that at the end our spring is stretched, so we're going to have some elastic potential energy. But what we could do now, we have a gravitational potential energy on both sides of our equation. We can pick 0 to be anywhere we want. So let's make our lowest point have 0 gravitational potential energy, and that's going to happen at the end. Alright, now we can rewrite this equation. We have our gravitational potential energy in the initial state. We have our work done by non-conservative forces. Let's not forget that's going to be a negative number. And at the end, all of our energy is in the spring. Okay, much simpler now. Let's take a look at how we punch those numbers in.